Hi students, it's Miss Bronner. I wanted to go over a couple of the two kinds of practice problems that you need for week 5 assignment. So you might be asked to use either the combined gas law here, which involves two of everything, one pressure, another two volumes, two number of moles, two temperatures. Now, not all circumstances require both things, and so you have to be able to decide what you're given in the problem. And the other one is what I like to call Pivnert, which is just one pressure, one volume, R, which is always a constant. It's the same 1.0821, has this complicated set of units, and then a temperature. And so this is lists what all of those things stand for. The other thing that you need to consider for these problems is that the temperature has to always be converted into Kelvin. And so you always do that by adding 273 to a temperature that's given in Celsius. And for the Pivnert problems, you need to use liters, atmospheres, and Kelvin. For the combined gas law, you could use a different unit of atmosphere, or you could use milliliters instead. You still have to use Kelvin. Okay, so let's look at this first one. It's at 1.33 atmospheres. A gas occupies a volume of 6 liters and has a temperature of 21.5 degrees Celsius. How many moles does this gas contain? And so I want to start by highlighting what is given. So we'll start with this. Atmospheres. That is a pressure. And then I have 6.00 liters, and that is my volume. And I have 21.5 degrees Celsius, and that is a temperature, which I'm going to immediately convert into Kelvin by adding 273 to it. And then the question says, how many moles? And so moles is going to be my unknown. And then R is going to be the same thing every time. Then I'm going to plug all of this into my Pivnert equation right over here. So here's the equation I'm using. Now I'm going to plug in my pressure, 1.33 atmospheres. This goes here, and then it's times the volume, 6 liters, and equals N, that's my unknown, 0.0821 liter atmosphere mole Kelvin. Remember that this is not an equation you plug numbers into. It's just a complicated set of units that go with this constant of R. And notice the units matter, though, for this problem, and then 294.5 Kelvin. So I multiply 0.0821 and 294.5, I get 24.18. I multiply 1.33 times 6, and I get 7.98. And then I divide both sides by whatever's with my unknown. So both sides get divided by 24.18. So that becomes 0.330 moles, and that is my answer. That is a Pivnert problem, and now I want to look at a combined gas law problem. And so that's going to use variables of more than one pressure or more than one volume or more than one temperature, and you have to figure out one of those. So let's start by writing down what is given. So I went ahead and highlighted the information that is given, and now I'm going to write it down. So I have 3,560 millimeters of mercury. And the tricky thing is you have to know that that stands for P. So that is my P1. And then I have another final pressure. It says, what is the final pressure? So that is my unknown. And then highlighted in kind of blue, or I have a T1, which is 500 degrees Celsius. And I'm going to change it to Kelvin by adding 273. So that's 773 K. And then I have a T2, it's 0. It's easy math to do. 273 equals 273 Kelvin. So that's my T2. And then I'm given an initial volume, so that's my V1, of 566 liters, and a final volume of 75.0 liters. So now I have everything set up, and I can plug this all into the equation. What I don't have is number of moles, and it doesn't change, so I can just leave it. If it's the same on both sides, then it just cancels itself out. So I can start by plugging in the numbers. 3560 times volume 1, which is 566, over my T1, which is 773 Kelvin, equals my second pressure, which is X, my second volume, which is 75 liters, over my second temperature, which is 273 Kelvin. So now I have to solve for X. There's a lot of different ways to approach this problem algebraically. What I usually do is I multiply all of these numbers times each other. 3560 times 566 times 273, and then I multiply these numbers and sort of, I guess we'll say, flatten out this equation. So I have 3560 times 566 times 273 equals X times 75 times 273. I'm going to put these numbers into my calculator, and this is what I'm going to get. I definitely get a huge number for this first one. I'm going to get something like 550,084,080 equals times 20,475. Now I'm going to divide both sides by what is with the X. So I'm going to divide that big, huge number by 20,475. And I get that X equals 26,866. If I was rounding it, I would round it to 26,900. But if you wanted to leave it like that, you definitely don't need decimal numbers, though. Then that would be it. You might have a tendency to think that this final answer is ridiculously huge, but it's really not. You're talking about the pressure that's being exerted by the gases inside this container, a steel container, by the way. So I took a original pressure, which is about a little over 4 atmospheres, and I took a volume and I took it from 566 liters all the way down to 75 liters. That's a lot of compression. And so that means there's going to be a whole lot more collisions than there would be as well, even though you did take the temperature down quite a bit. It's probably good. You don't want to burst the steel drum.